So let's start with the step response of a second order transfer function. Let's assume that the input is a step input of magnitude m. We go through the standard exercise of multiplying the transfer function with the Laplace transform of the input. If zeta is greater than 1, this is the response in time domain of a second order transfer function. And as you can see from the graph here, as you increase the value of zeta, the response gets slower and slower. On the other hand, as you decrease zeta, the response gets faster and faster. If zeta is equal to 1, we get the fastest response from a second order transfer function with no oscillations. The tau1 and tau2 in this expression here are the roots of the denominator polynomial. We're going to learn later on that these roots are also called the poles of the transfer function. If the process is critically damped, then the response is given by this time domain expression, and the response is almost indistinguishable from that of a first order transfer function. If the process is underdamped, this is a case that is a lot more interesting, because if the process is underdamped, zeta is going to be between 0 and 1, and the response will not only have an exponential term but also have a couple of trigonometric terms. And these trigonometric terms contribute to oscillations in the response. You will notice that with this type of a response, as the zeta decreases, you'll observe more and more oscillations in the response. The time it takes the response to reach the final steady state for the first time is what is called rise time. The time it takes the response to reach its first peak, or the maximum value, is time to peak, TP, and the time it takes for the response to reach within 5%, plus or minus 5% of its final steady state value, is what is called the settling time. Now, if zeta is negative, you can very easily show that the roots of the denominator polynomial of the transfer function are going to be positive, and therefore the transfer function itself is going to be unstable. In other words, this exponential term here is going to have a positive power, which will lead to exponential growth in the output. If zeta is less than 0, the response, for instance, could be an unstable oscillatory response, as shown here. What is interesting to note is that there is no zeta in a first order transfer function, and therefore first order transfer functions are in general going to be stable as long as the time constant is positive. Now, those are some useful and interesting observations about first and second order transfer functions. Now, it turns out that those same observations can be extended to very high order transfer functions, because in practice we will not only see first and systems whose dynamics are defined by first and second order transfer functions, but we'll also see systems whose dynamics are defined by higher order transfer functions. So what we would like to do in chapter 6 is define two new quantities called poles and zeros to study or relate the behavior of higher order systems to these poles and zeros. We want to relate poles and zeros to the behavior, dynamic behavior of higher order systems. We are also going to study processes with time delay and look at some approximations of these time delays. It turns out that designing a controller using a time delay is not a straightforward exercise. Before we get into the details or the definitions of poles and zeros, I would like to give you some quick background on complex numbers, because we're going to see these complex numbers again and again. In Cartesian coordinates, a complex number is represented by x plus jy. On a Cartesian plane, we can use x-axis to denote the real part of the complex number and the y-axis to denote the imaginary part of the complex number. The complex number x plus jy is going to be located somewhere over here. It'll have a magnitude of square root of x squared plus y squared, and it'll make an angle of theta with the positive real axis. And that theta is given by tan inverse of y over x. The same complex number can be represented using polar coordinates, r times e power j theta, where r is the distance of the complex number from the origin, square root of x squared plus y squared, and theta is again tan inverse y over x. And the reason we want to study complex numbers or understand complex algebra very well is because Laplace variables are, after all, complex variables. Now, in order to motivate you to understand the significance of poles and zeros and relate them to the qualitative behavior of responses of transfer functions, let us first take a look at certain familiar transfer functions. First order plus time delay transfer function of the form k over tau s plus 1 times e power minus theta s, or tau ds, where tau d is the time delay. And a second order transfer function of the form k over tau square s square plus 2 zeta tau s plus 1 times the time delay. Now we want to ask the question, what happens if we have a generic general transfer function? We have already derived the responses of first and second order transfer functions to a variety of inputs. We want to ask the question, is there a way to extend our understanding of first and second order transfer functions to generic transfer functions of any order, of order greater than n greater than 2? For these transfer functions, we're going to assume that n is greater than or equal to m, where n is the order of the denominator polynomial and m is the order of the numerator polynomial. You might recall that all causal transfer functions satisfy this property. In other words, all causal transfer functions have a numerator order that is less than or equal to the denominator order. If that's not the case, then we run into systems that are called non-causal systems. So for instance, s squared plus 1 over s cubed plus 2s plus 1 is a causal system, and these are physical systems. They occur in nature. On the other hand, the inverse of it, which is s cubed plus 2s plus 1 over s squared plus 1, it is hypothetically possible to have a transfer function like that, but you will never find a system that behaves according to that transfer function, because those transfer functions correspond to non-causal systems where the future affects the past, which is something that we never see in reality, in practice. Future never affects the past. It's only the past that affects the future. And therefore, all realistic transfer functions have a numerator order that is less than or equal to the denominator order. Now let's take three simple first-order transfer functions and relate the location of their poles to their qualitative behavior. We already know that a transfer function with a smaller time constant responds faster, and a transfer function with a larger time constant responds slower. We can make a few observations from these graphs. Larger tau leads to slower response. Smaller tau leads to faster response. And notice that the roots of the denominator polynomial equation for each of these transfer functions are at s equal to minus 1 over 10, s equal to minus 1 over 20, and s equal to minus 1 over 5. We can plot these on a complex plane with the real part on the x-axis and the imaginary part on the y-axis. These three roots are real, and therefore they are going to lie on the real axis. They're all negative, therefore they lie to the left of the imaginary axis. And we now know that as these roots move away from the imaginary axis, the process gets faster. In other words, there is a clear correlation between the location of these poles and the way a process responds. And therefore, it only makes sense to give them a name. And the roots of the denominator polynomial of a transfer function are called poles. Let's try to do the same with the second order transfer function, the standard second order transfer function. The roots of the denominator polynomial of a second order transfer function are s1, which is minus zeta over tau plus square root of zeta squared minus 1 over tau, and s2, which is minus zeta over tau plus square root of zeta squared minus 1 over tau. Now you can find roots of any polynomial in MATLAB using a function called roots. Now we've obtained these roots using the standard formula for solving a second order polynomial equation. Remember that it is possible to express only first and second order, the solutions of only first and second order polynomial equations analytically. If you have a higher order polynomial equation, it is simply not possible to derive an analytical expression. Instead, you have to use the MATLAB function roots. If zeta is greater than 1, S1 and S2 are real and unequal. We have an overdamped response. If zeta is less than 1, then S1 and S2 are going to be complex roots and we have an underdamped response. If zeta is equal to 1, S1 and S2 are real and equal and the response is going to be critically damped. Observe carefully the location of these roots and the corresponding response. If the two roots are to the left of the imaginary axis and on the real axis, then the response is going to be overdamped. If the two roots are overlapping or on the left hand side of the imaginary axis or on the real axis, then the response is critically damped. If the two roots are complex conjugates and not on the real axis but to the left side of the imaginary axis, then we have an underdamped system. So it must be obvious by now that we are able to relate the location of poles and poles to the corresponding qualitative behavior of a transfer function. And it turns out that this observation can be extended to processes with transfer functions of any order. The roots of the denominator polynomial of a transfer function determine its dynamic response. So the poles are defined as the roots of the denominator polynomial of a transfer function of any order. Similarly, one can define zeros that are the roots of the numerator polynomial of a transfer function. It turns out that zeros do not affect what are called the response modes of a transfer function. Instead, they affect only the coefficients of those response modes. Let me illustrate this through a simple first order example. Let's consider a transfer function of the form shown here. This is said to be a lead lag transfer function. The denominator polynomial corresponds to a lag and the numerator polynomial corresponds to a lead. Or in other words, denominator polynomial slows the response, the numerator polynomial speeds up the response. That's why this transfer function is called a lead lag element. Km, tau a, and tau 1 are some constants. There is a zero for this process at negative 1 over tau a. There is a pole at negative 1 over tau 1. And these are, of course, the roots of the numerator and the denominator polynomials. If we try to find the step response of this system, we end up with the following time domain expression that includes an exponential and a constant term. Now we can replace this expression and write it in terms of the poles and the zeros. And you will notice that the exponential term, which represents the mode of the response is typically an exponential term or a cosine or a trigonometric function or time itself. However, the zero appears only in the coefficient of this response mode. So that's the distinction between how zeros and poles affect the response of a process. We can extend this observation and these results to a higher order system. For example, consider the following response of a third-order transfer function. Following step response of a third-order transfer function. Clearly, the s in the denominator of this response must correspond to the step input. The remaining part of this response must correspond to a transfer function. We would like to locate the poles and identify their response modes in time domain. We're going to use the standard approach, which is to find the partial fraction expansion of this polynomial fraction and write y prime s as the sum of 4 different fractions, where zeta is less than 1. S1 and S2 are two roots of second order denominator polynomial, and alpha 1, alpha 2, alpha 3, and alpha 4 are appropriate constants. The inverse Laplace transform of the first factor, or the term, is alpha 1 times the step response. Now that corresponds to the following interpretation. In Laplace domain, alpha 1 over s has a pole at 0, and in time domain, it seemed to correspond to a constant. The second term, alpha 2 over tau 1 s plus 1, corresponds to an exponential term in time domain. And the following interpretation is true for this mode. In Laplace domain, this particular term has a pole at negative 1 over tau 1. Remember or notice that this pole is negative because tau 1, the time constant, is always positive, and it corresponds to a stable exponential term in time domain. Now moving on to the third term, which is alpha 3 over s minus s1, its inverse Laplace transform is again going to be an exponential term, but with a difference. Given that zeta is less than 1, s1 and s2 are going to be complex numbers. And therefore, the inverse Laplace transform of the third term is an exponential to a complex term, which one can simplify using complex algebra into an exponential term multiplied by a complex number that involves cosine and sine terms. The amplitude term, which is a function of the exponential, dictates the oscillations, the amplitude of the oscillations, and the cosine and the sine terms contribute to the oscillations. Now, if x is less than 1, as shown here in the green curve, the amplitude is going to be stable, and therefore we will see stable decaying oscillations over time. If x is equal to 0, then the exponential term will be equal to 1, and we will see sustained oscillations over time, non-decreasing oscillations for x equal to 0. And if x is greater than 1, the exponential term is going to explode over time, and therefore we will notice unstable increasing amplitude oscillations. In other words, we can conclude from this third term that complex poles in Laplace domain lead to oscillations. And for the fourth and the final term, we again have an exponential term to the power of a complex number. And this complex number is the conjugate of the previous root s1. There seems to have been a typo here. On the left-hand side, we should have alpha 4 over s minus s2, not s1. We can come to the same conclusion as with the previous root. Complex poles lead to cosine and sine terms in time domain and oscillations in response. It turns out that there are certain processes where the response could naturally be unstable or explodes with time, even if the input is stable and is not exploding with time. One of those transfer functions is given here. It's 1 over s minus 2. Let's try to find its response in time domain. It has a pole at s equal to 2, and the step response can be obtained by simply multiplying the transfer function with the Laplace transform of the step input. After going through the standard algebra, you'll notice that the response is given by negative 0.5 times the step plus an exponential term, which explodes with time. What you will notice is that the pole of this transfer function is actually at 2, which is on the right-hand side of the imaginary axis. And it turns out that this pole P on the right-hand side of the imaginary axis also corresponds to an exponential, and because P is positive, it's on the right-hand side of the imaginary axis, it's on the positive side of the real axis, and therefore the exponential term is going to go to infinity with time. So this leads us to conclude that if the pole is on the right-hand side of the imaginary axis, the response is going to be unstable. There's one other final response I want to explain, and that is the inverse response. It occurs when the initial response to a step input is in one direction, but the final steady state is in another direction. Let's consider a process with a step input as shown here on the left-hand side. The typical response is shown on the right-hand side. But for processes with inverse response, the initial response is going to be in the negative direction, and the eventual response is going to be in the positive direction. A good example of this inverse response is boiling water to generate steam. If there is a sudden increase in steam demand, which can be approximated as a step change, the steam pressure in the boiler initially is going to drop. And that will result in more evaporation, leading to the formation of bubbles on the surface of water, which will artificially increase the level in the boiler. This level sensor is going to notice or read an increase in the level because of the excessive formation of bubbles due to the increased rate of evaporation. But once the pressure reaches its new equilibrium, the water level is going to drop. And that is because you're now drawing more steam out of the boiler. When you're drawing more steam out of the boiler, you would naturally expect the level of the water to drop. If you were to plot the level versus time for this process, it is going to look like the graph shown here. The level is going to initially increase artificially because of the bubbles formed at the surface of the level, but eventually the level is going to drop and reach a new steady state. So processes with zeros in the right half plane exhibit inverse response. Now let me define a stable process. We call a process stable if a finite change in input results in a bounded or finite change in the output, as shown in the graphs on the right-hand side of the process. This process, if it's stable, could result in an unstable response if the input itself is infinite or unbounded. That is acceptable. But as long as the process gives you a bounded finite response to every bounded finite input, then the process is said to be stable. All that we have learned so far, we can conclude that stable processes have all poles in left half plane of the complex coordinate system. Unstable processes are those where the response could be unbounded even for bounded inputs. So for instance, if you have a bounded step input and if the response is unstable, it goes to infinity, unbounded, then you have a process that is unstable. And unstable processes, it turns out, have at least one pole in the right half plane. An unstable process does not necessarily have to have all its poles in the right half plane. It just needs to have a single pole in the right half plane for it to be considered an unstable process. And a process with poles on the imaginary axis is said to be critically stable. So critically stable processes are on the verge of becoming unstable, but they are not unstable by the pure definition of instability or unstableness. Critically stable systems provide bounded outputs, even for bounded inputs. The output does not go to infinity, and therefore they're not really unstable systems, but they're said to be critically stable on the verge of becoming unstable. And it turns out that the good news is very few chemical processes are actually unstable. However, it's an important concept required in understanding the behavior of these processes in conjunction with controllers. In the next lecture, we're going to look at an example on how instability might arise in a process. Here's the intuitive idea. If you have a simple tank with an inlet flow rate and an outlet flow rate, and you design a controller where the controller increases the flow rate when the height of the tank is greater than the desired height, or if it does exactly the opposite of that, where the controller decreases flow rate when the height of the tank is less than the desired flow rate, the controller would actually be doing the opposite of what one needs to do in order to push the height towards the desired set point. When it does that, the opposite of what it's supposed to do, eventually what's going to happen is that the liquid is going to overflow the tank, and therefore it is considered an unstable system. So to simplify this, let us suppose that the desired height is less than the height of the tank, and your controller decides to open up the valve. Now, the height is never going to reach the desired height because the height is already greater than the desired height, and to deteriorate the situation, the controller has opened up the valve, you're adding more liquid to the tank, the height is going to continue to increase, and your controller is going to continue to open the valve because that's what it is programmed to do, eventually leading to a major spill. In other words, the system overall is going to be an unstable system.
Okay, so now let's move on to approximation with time delay. As I mentioned earlier, a major disadvantage with time delays is that they appear as irrational factors involving exponentials in Laplace domain, and when they appear in the denominator polynomial of a closed-loop transfer function, it makes it very hard to find poles and relate them to their qualitative behavior, as we had done many times in this chapter. There are two types of approximations that one can make with time delay. One is polynomial approximation of e power minus theta using first-order Taylor series expansion. Expand the exponential term as a Taylor series and then chop off all the terms involving a square or higher order polynomials. You'll end up with 1 minus theta s. This is what is called a first-order Taylor series approximation of the time delay, and it's only valid for small values of theta, as you might imagine. The Pade approximation, on the other hand, is a slight variant of the Taylor series expansion. It turns out that the Pade approximation is better than the first-order Taylor series approximation. I just want to remind you as to when and where and how time delays occur. They occur as a result of material being transported from one location to another location. This is often how time delay or transportation delay occurs in chemical engineering processes. And it's in Laplace domain, it is simply obtained by multiplying the original signal with an exponential term. Many high-order processes, such as an overdamped second-order process, can usually be approximated using a first-order plus time delay transfer function. And this is often done in practice because it is much easier to design controllers for lower-order transfer functions than it is to design controllers for higher-order transfer functions. And the sheer simplicity of a first-order transfer function is also quite appealing, and therefore, in practice, engineers often approximate even higher-order transfer functions with first-order plus time delay transfer functions. Now, using a graph, I would like to show you why it is possible to approximate a higher-order response with a first-order plus time delay response. Why is this approximation even possible? That's a typical first-order response. And that is a typical second-order overdamped response. And if you have an even higher-order response, you will see a response like that. The response shown in black. Now, it is easy to see that we can shift the first-order response by a certain delay and get an approximation of the higher-order response. This is obviously an approximation, therefore there is going to be certain error in the initial stages. There is going to be error throughout, but more in the initial stages. The initial slower response distinguishes higher-order processes from first-order processes. And therefore, it's possible to approximate the higher-order transfer function with a delay followed by a first-order response. Here is an example where I want to show you how time delay can be approximated to get a transfer function that provides a response that is very close to the unapproximated transfer function. I don't know if there's a word called unapproximated, but the original transfer function. We can use Pade approximation and replace the exponential function in the transfer function with a a first order with another transfer function involving only polynomials. Clearly, this new transfer function has a 0 at 2 over theta, although the original transfer function has no zeros. It also has a pole, not only one pole, but two poles, unlike the original transfer function, which had only one pole. The approximation of the original first order plus time delay transfer function led to a second order transfer function with a 0 in the right half plane and two poles in the left half plane. Now, because it has a 0 in the right half plane, it is likely to lead to an inverse response. That is the original first order plus time delay response, and the pink line here represents the response of the approximation obtained by approximating the time delay. In this process, what we have done is eliminated the time delay and replaced it with an inverse response, an approximate inverse response. Remember, zeros in right half plane typically lead to inverse response. So that's the end of chapter 6. We've tried to extend our understanding of first and second order systems to higher order systems in chapter 6. Now we're going to move on to the more exciting stuff on designing controllers, on feedback control systems. So this is an appropriate time for us to take a step back and look back at the path we had taken to come to this, to arrive at this point in the course. We started off with modeling processes and derived ordinary differential equations, which we then used Laplace transforms to convert those ordinary differential equations into transfer functions using simple algebraic manipulations. We've then used poles and zeros of transfer functions to relate, to describe the dynamic behavior of these transfer functions. So now we know how different types of processes behave. And that understanding is what we're going to use to design feedback controllers. In particular, in chapter 8, we're going to look at proportional, integral, and derivative controllers. Eventually, we're going to put these three controllers together to develop a new controller called a PID controller. The PID controller incorporates the advantages of the three controllers, P, I, and D controllers. In the next lecture, we're going to look at the typical components or the basic components of a standard feedback control loop. We're going to do this using the blending tank example. And in the tutorial, you had already looked at the basic components of a feedback control loop that included a sensor. In your case, in the tutorial, the sensor is a temperature sensor. The controller is the Arduino board, and the final control element or the input to the process is the voltage coming out of the Arduino board. The process itself was the transistor.